Hi, in this video I'm going to be giving a basic guide to top-down assignment in AutoVectis. For this demonstration I'll be processing a myoglobin top-down file collected on a Bruker instrument, so we'll start with the Bruker file and process on from there. So first of all, we'll open the Bruker file in AutoVectis and convert it into absorption mode. Conveniently, it was the last file that I processed, and when you open AutoVectis, it remembers the last set of settings and refills all the controls with those. So here's the file we're going to process, but if we wanted to change that, we just use the Browse button next to the file path control. On this row, we're using the default 2 0 pads, and I've set the mass range from 100 to 3 kilodaltons. I'll be using the default DPAC apodization and the default F value of 0.5. And we'll be running this in recalculate mode, which means that AutoVectis will solve the phase correction function based only on information in the file, and not because it has a pre-saved AMP value in it. So all we have to do is click begin, and AutoVectis will phase the spectrum for us. And that's it, the spectrum's now phased, so we can detect the peaks in it. And I'll slightly drop the SNR value. So now we have our absorption mode spectrum and the peaks have been detected in it, so we can export that to AutoSeequer for assignment. To do that, we need to jump to the Spectral Info tab and then click the Export to AutoSeequer button. AutoSeequer does assignment against library files, so here it's asking us which library we want it to use. It has a module called AutoFragger, which is used for making individual libraries or even batches of libraries. But for this demo, I've already made a library, and you can see it in the folder here with the suffix sqlib. It has the SQ in the file type because, like all the libraries used in AutoVectis, it's an SQLite file. And that means you can open them and browse the contents in any SQLite browser. But for now, I'll just open that library so AutoSeequer can continue processing. We can see in the sequence map that AutoSeequer has uploaded the protein sequence, but it hasn't found any fragments yet because we haven't told it what kind of fragments to look for. You can pick these in the Fragment Classes to Search tab. As this is ECD data, we'll choose C' and Z dot. And it looks like AutoSeequer has found a whole lot of fragments. But that's because we've been searching a really wide mass range, because we don't know what the mass recalibration on this spectrum is yet. So if we jump to the Mass Errors tab, we'll be able to have a look at those and work out how we could recalibrate this data. Looking on the mass error by mass plot, it's easy to see where the real assignments are. So as would be expected, we are going to need to recalibrate this file, and luckily AutoSeequer makes this easy by letting us use some cursors on this plot to generate a quick recalibration line. And with that basic manual recalibration, we can now research the data over a much smaller mass range. It looks like I did a pretty good job with the manual recalibration. But it is still a manual by eye recalibration, so we'll want to do a proper one, and we do that on the AutoCal tab. Using this tab, we can apply a polynomial recalibration function. And we can define the order of that polynomial on the order of fit control. These lists are automatically populated with all the detected fragments. And you can easily delete those fragments you don't want to use for calibration. But the normal route would be to use all of them. And in this indicator, you can see the old recalibration line and the new one that AutoCal is recommending. And to accept this recalibration, we click the Accept AutoCal button. With this improved recalibration, we can now repeat the search over an even smaller mass error range. So how's that affected the sequence map? Well, it looks like it's done a pretty good job, and one of the ways I can tell that is that we're not seeing any fragments before proline. AutoSeequer doesn't automatically discount fragments before proline because they can be a really useful way of giving you a feel of how reliable your assignments are. While we're looking at the sequence map, we can see that all the fragments are shown in red. You can change that colour using the colour box up here. Or you can convert the sequence map into heat map mode. In this heat map view, the colour of the fragment tick tells you how many charge states the same fragment was detected in. Currently it's set to go from violet to red in rainbow order, so a violet tick indicates that a fragment was seen in a single charge state, blue means 2, green means 3, and so on all the way up to red in 6 or more charge states. Having carefully assigned all these fragments, we need to have a way to export that information so we can review it later or to produce figures. We can export the assignments to an sqassignments file on the Import Export tab. As with the sqlib format, the sqassignments format is also an SQLite database, so you can open and review them in any SQLite browser. We chose this output format because it will make it easy to plug in to downstream bioinformatics pipelines. Most programming languages, such as Python or R, already include libraries to make it easy to load and process data in SQLite format. But you can also export all the assignments to Excel. Finally, for this demo, if you want to save the sequence map as a figure, then you can do that by clicking the Save Seq Map button. This will save the sequence map as an SVG format vector file that you can open in Inkscape or Illustrator or other similar graphics programs and save into any format you like. As the sequence maps are saved in vector format, they can be easily scaled up to large sizes for use in posters. So, I hope this demonstration of the basic top-down capabilities of AutoSeequer and AutoVectis have been useful. As usual, if you have any questions, you can contact us on autovectis@gmail.com, or you can speak to any member of the SpectraSwiss team directly.